Hi everyone, welcome to APCP String Seminar. It's my honor to introduce today's speaker, Professor Steve Carlip from UC Davis. Today he will give a talk about Schwarzian on the stretched horizon. Please join me in welcoming our speaker, Professor Steve Carlip.
Okay, well, thank you for the invitation. Please let me know if you have any trouble hearing me. I've just recovered from a case of COVID and my throat is still a little bit stuffy. I'm going to talk about an effective description of the degrees of freedom of a black hole. This is one small part of a very large and very active research program that's had hundreds and hundreds of papers written in the past few years. And I should say at the beginning that I am not an expert in this whole program. And so I'm sure that if you try, you can easily come up with questions that I can't answer. So, like most talks about quantum gravity and black holes, I'm going to start with the fact that black holes are thermodynamic operators. And in particular, we've known for 50 years now that they have an entropy proportional to the horizon area. It is natural to suppose that this entropy, like other normal entropies,
Question?
comes from...
Excuse me, I think the slide is not going to the other. We are seeing only the first slide still.
Really?
Yeah.
Okay. Let me try to figure out. You're still only seeing the first slide?
Yes, only the first slide.
Okay. Let me try something different.
No, yeah, it's
Okay. Okay, this is Zoom being strange again. Nothing unusual about that. Okay, so now you're seeing it. Let me just check. If I move to the next slide, do you see that? Yes.
Yes, it's
Okay,
moved.
so it's only when I'm in full screen that you can't see the slide changes I see. Okay, so to continue, we know that black holes have an entropy. It is natural to suppose that this, like other kinds of entropies, comes from some counting of fundamental quantum gravitational degrees of freedom. And so there are some natural questions. What are the degrees of freedom responsible for the entropy? Where do they live? And what happens with them as the black hole evaporates? This third question is the one that's been getting a whole lot of attention recently because it's tied up with the information loss problem, the problem of how the information inside a black hole escapes when the black hole evaporates in Hawking radiation. I will have absolutely nothing to say about that. I don't have anything new there. It's a really interesting question. Going backwards, the second question is, where do the degrees of freedom live? And there are two natural guesses. One is that they're at infinity, as in the ADS-CFT correspondence. And the second is that they're at the horizon or at some sort of horizon of the black hole. These two are not necessarily exclusive. It could be that there's a dual theory at infinity that describes a bulk theory that includes degrees of freedom associated with the black hole horizon. I'm going to assume that something at least vaguely like that is true, that it's at least possible to associate degrees of freedom with the black hole horizon. As for the first question, what are these degrees of freedom? Probably a complete answer to that takes a full quantum theory of gravity. But it could still be true that we can write down effective descriptions of these degrees of freedom that give us a lot of information. Let me explain what I mean by that. The Einstein-Hilbert action is invariant under diffeomorphisms. And what that means, probably at least in a quantum theory of gravity, is that states that differ by a diffeomorphism are identified. They're considered the same physical state. Or equivalently, that excitations that are pure diffeomorphism are non-physical. They're not part of the physical degrees of freedom. But if you have a boundary, then typically boundary conditions are going to break this invariance. For example, if you have a fixed boundary, diffeomorphisms that are transverse to the boundary, that move the boundary, will change the boundary conditions. As a result of this breaking, you at least potentially have new states, edge states, which are states that would normally be all identified as a single state from diffeomorphism invariance, but now split into a set of states because the invariance is broken. I should say that when I talk about a boundary, I don't necessarily mean a physical boundary. What I mean is a place that you impose boundary conditions. For instance, if you're asking a question in quantum gravity about a black hole, you have to specify that there's a black hole with certain properties. And typically what that means is that you say there is some surface, which is a horizon that has a certain area that has vanishing expansion. That's imposing boundary conditions, and that breaks the diffeomorphism invariance. Now, these edge states have shown up in a number of different contexts. They're completely vital in Chern-Simons theory, for instance. And it's been shown that they're necessary for gluing. That is, if you want to, if you have two manifolds with boundaries and you want to join them along the boundary by integrating over boundary values of the fields, you have to include an integral over the edge states, or you just don't get the correct composition. It's useful to compare this picture to the standard picture of Goldstone bosons. This is not exactly the same, but in spirit, it's very similar. As in the appearance of Goldstone bosons, you have a symmetry that's broken. As a result, there are new degrees of freedom that correspond to excitations from states that used to be equivalent under the symmetry. And as in the theory of Goldstone bosons, you can write down an effective description in terms of the symmetry breaking, even though the actual field content, if you have some spontaneously broken scalar field theory, for instance, and you want to actually write down the Goldstone bosons, they're going to be complicated functionals of the original fields, but you can get an effective description just from the pattern of symmetry breaking. Now, this idea in gravity dates back to about 1995, where it was first used in 2+1 dimensional gravity,
Excuse
where it's a special, yes.
May I ask an elementary question? In the previous page, you mentioned about Goldstone bosons. I'm somewhat confused because diffeomorphism invariance breaking is basically local symmetry breaking, but
yeah,
as you know, it's global symmetry. Local symmetry is just a redundancy, just reparameterization, blah, blah, blah. But
right.
So is it a physical degree of freedom, such edge mode?
The edge modes are physical degrees of freedom. When I talked about Goldstone bosons, I said that it was an analogy. These are not exactly Goldstone bosons because, as you say, it's a continuous symmetry. But they're not, the spirit is the same. These are genuine new degrees of freedom because the boundary conditions mean that states that used to be identified are no longer equivalent because of the breaking of the diffeomorphism invariance. They aren't Goldstone bosons. That's just a more familiar context that can give you some idea of what's going on.
I see. Let me consider it more. Thank you.
Okay. Okay, so the first use of this came in 2+1 dimensions, where that's actually an easy way to see that they're physical degrees of freedom because 2+1 dimensional gravity on a manifold without boundary has no local degrees of freedom. But when you write it on a manifold with boundary, there is an induced Wesson-Witten model at the boundary, which actually has been used to try to count states of black holes. But the recent excitement about this came from a paper by Maldacena, Stanford, and Yang about 5 years ago, who looked at two-dimensional gravity and at what they call nearly anti-de Sitter space, which means anti-de Sitter space, but with the boundary at infinity moved slightly inward to an arbitrary curve, small distance from a small conformal distance from infinity. And what they showed is that the resulting effective theory, which describes the shape of this boundary and therefore characterizes the diffeomorphisms normal to the boundary that could move it. The effective theory is described by a Schwarzian action. And this has led to, as I said, hundreds and hundreds of papers with all sorts of really interesting and deep results relating this theory to matrix models, to the SYK model in condensed matter, leading to some of the first recent real progress in this question of information loss.
I have a question.
Yes.
So when you say that the boundary has just been pulled in, is it something like a conformal compactification?
It is not. It is, if you like, you can think of it as starting with a conformal compactification, but then various fields go to infinity at conformal infinity. And so you can regulate them by putting a new boundary just inside the compactified, the conformally compactified boundary.
Okay, thank you.
And then this new boundary has an arbitrary shape. And the resulting, the degrees of freedom that are described by the Schwarzian action are basically the shape degrees of freedom of this boundary.
Okay, I understand. Okay.
So it really does look something like this picture where the circle is the conformally compactified infinity and the wobbly line is this new boundary.
Okay, thank you.
Okay, so let me just pause for a second since I'm talking about the Schwarzian action and remind you what the Schwarzian derivative is. It's a particular combination of first, second, and third derivatives that appears everywhere. This was actually first discovered by Lagrange in 1781 in a paper about mapping the Earth. It comes up in complex analysis, in one-dimensional dynamics, Teichmuller theory, theory of ordinary differential equations, theory of integrable systems. In two-dimensional conformal field theory, the transformation of the stress energy tensor under a finite diffeomorphism is given by the Schwarzian derivative of the parameter that describes the diffeomorphism. Let me mention for future reference that the Schwarzian derivative is really a quadratic differential, that is a rank 2 symmetric tensor, that it should really be thought of as the Schwarzian of f times d tau squared. The Schwarzian action, the one that shows up in this work of Maldacena et al., is basically just an integral of f dot squared plus the Schwarzian derivative times an extra scalar field, which acts as a Lagrange multiplier. This appears in various forms. If you change variables, you can get rid of the f dot squared, but that's the basic quantity. It gives a one-dimensional quantum theory, which can be analyzed in great detail. The partition function, the correlation functions, so on, can all be solved. It can be written as a matrix model, and that gives you very fine details about the spectrum. You can do a tremendous amount with this. So that was background. What I'm going to focus on for the rest of this talk is one particular small question within this context, which has to do with getting back to the relationship with black holes. Now, the Schwarzian theory that Maldacena and his collaborators found that's created all of this interest comes from two-dimensional gravity, specifically a model called Jakob-Teitelbaum gravity, in asymptotically empty de Sitter space. There's not an obvious relation to black holes, although that theory of gravity does have solutions that are black holes. But it's actually more general than that. Generically, if you have a near extremal black hole, then the region near the horizon can be approximated as an empty de Sitter space with description in terms of Jakob-Teitelbaum gravity. So these hundreds of papers all really are about black holes, black hole degrees of freedom, but only about the extremal and near extremal cases. And so the question is whether whether you can say anything about generic black holes. Is there any way to give a description of an arbitrary black hole in terms of some effective degrees of freedom that perhaps have a Schwarzian action as their description? So to get there, we need a few steps. Step one is to get from our arbitrary d-dimensional black hole to 2 dimensions. First of all, what are the 2 dimensions? A stationary black hole has 2 preferred directions. There are the directions of the null generators of the horizon, that is the paths of photons that are trapped exactly at the horizon. That gives a null direction. And then there is the direction normal to the horizon at a fixed time. You actually don't really even need the condition of stationarity. What you need is something called an isolated horizon, which means a black hole in which an arbitrarily small region around the horizon is stationary. Then the same structure exists And that gives you two preferred directions, which are going to be the directions that we reduce to. Now, in the case that you have nice global symmetries, for example, for the Schwarzian black hole with spherical symmetry, we now know how to use standard Kaluza-Klein methods to reduce the Einstein-Hilbert action to two-dimensional action. But there have been a couple of really beautiful papers by Yun showing that you don't actually need the extra symmetry. That if you take an arbitrary metric and you write it in a Kaluza-Klein-like form, and then work out the action, what you get is an effective two-dimensional action, which looks like two-dimensional dilaton gravity coupled to a bunch of gauge fields and a bunch of scalar fields. The difference between this and standard Kaluza-Klein is simply that now the gauge group is the whole group of diffeomorphisms of the transverse directions. It's a big gauge group, but that's okay. So this gives us an effective reduction near the horizon of a black hole to a two-dimensional theory, which looks like dilaton gravity, that is like the standard Einstein-Hilbert action, but with an additional scalar, the dilaton, which physically from the higher dimensions is the transverse area. It's the square root of the determinant of the metric in the directions transverse to the horizon. So that's step one. That gives us a two-dimensional theory. Step two, we would like to understand the near horizon. Yes.
For in the last the previous slide, you how can you determine this potential? And is there like if there is some many local minimum, is there can you also consider some phase transition there, or like there is like
the specific form of the potential depends on the details of the theory that you're dimensionally reducing. So for example, for the Schwarzschild black hole, V is just 1 over square root of phi. For the near extremal black hole, V is just a constant times phi. For higher dimensions, for Kerr black holes or black strings or black rings, you still get this general form, but the potential depends in a complicated way on exactly what the starting theory was.
So can you
Fortunately,
can you tune the potential so that there is some many local minimum of the dilaton potential, and can you also consider some transition between this local minimum?
I don't know offhand. It's possible that you could, by choosing well, let's see, in the two-dimensional theory, you have these extra gauge fields that also couple to the potential, and there might be solutions of those which would correspond to solutions of the transverse metric that might give you strange-looking potentials. I mean, I should say that I talked about Schwarzschild and Kerr and near extremal and so on, but this formalism works fine if you have what's called a dirty black hole. That is a black hole that's surrounded by other kinds of matter which can distort its horizon. So probably you can do that by just setting up a distorted enough horizon, but I'm not sure.
Thank you.
Okay, so to understand very clearly, this gauge fields, they somehow appear in the potential V5 that you have written?
Well, no, there's this plus dot dot dot. If you choose co-rotating coordinates, then the additional gauge field terms, which look basically just like Kaluza-Klein gauge fields, they're 0 at the horizon and order rho squared away from the horizon, where rho is the proper distance. So near the horizon, they're there, but they can be safely ignored.
Okay, thank you.
If you want details about that, I have a paper from a couple of years back about BMS symmetry for a generic black hole near the horizon for generic black holes that goes through this reduction in painful detail. If you
Okay.
look at the appendix.
Okay, thank you.
Okay, so the next step is to look at the near horizon geometry. Again, for special cases, this is well known, goes back to Gibbons and Hawking in the early 1970s, that it's known that you can choose coordinates so that the geometry near the horizon of, for example, a Schwarzian black hole looks like Rindler space, that is like flat space-time, but in coordinates that describe an accelerating observer with an acceleration equal to the surface gravity of the black hole. There's another under-recognized paper by Martin, Medved, and Visser who show that this is generically true for non-extremal stationary black holes, that you can always write the RT part of the equation, part of the metric, in a form that looks essentially like Schwarzschild. And you can always choose Rindler-like coordinates, which, if you then analytically continue to imaginary time, give you ds squared equals d rho squared plus rho squared d tau squared, where tau is a rescaled imaginary time, which has to have a periodicity of the inverse temperature of the black hole. In fact, that's one of the standard ways of deriving the temperature by using this metric and observing that the Green's functions have this periodicity. And so you get something that looks like flat space in the Euclidean continuation with the horizon at the origin at rho equals 0. The third step is that if we're looking at a boundary, in this case, either the horizon or a slightly stretched horizon, then typically the action requires boundary terms. Otherwise, the variation of the action isn't an extremal because you get terms from integration by parts that don't vanish and destroy the extremality of the action. Again, this result goes back to the 1970s, and there is a standard boundary term, the Gibbons-Hawking boundary term, which for this case looks like the integral of phi, the dilaton, times k, the mean curvature, the extrinsic curvature of the boundary. This is a boundary term suitable for holding the metric and the dilaton fixed at the boundary. In that case, with this term, the action really has an extremum. We'll come back to that choice a little bit later, but it's certainly a standard choice.
So here, when you say boundary, here it's maybe you have slide here. So when you say boundary, we usually consider boundary at infinity, but here you are consider boundary including some horizon.
Yes.
Also, is it Euclidean? It looks like a Euclidean, or are you considered Schwarzian, or it doesn't matter?
It's a whole lot easier in Euclidean signature. I'll come back. I'll say a word about that at the very end of the talk. Stretched horizons are actually very complicated in Lorentzian signature.
Okay, thank you.
Okay. So the boundary term, there are two ways of thinking about this boundary term. One is that if you look at the behavior of the action with this flat metric and with the Gibbons-Hawking boundary term, because the metric is not well defined at rho equals 0. That's standard for polar coordinates. And as a result, if you're very careful about all of your integration by parts, there is an extra boundary term at rho equals 0, even in the case that you don't have a stretched horizon. But the way to get that term is to consider the theory on a manifold with a stretched horizon, that is sort of flipping the picture of nearly anti-de Sitter space. We're now putting a small curved line right around rho equals 0, right around the horizon. And then you can take the limit. You can take that to be a circle and take the limit as its radius goes to 0. And the boundary term is not 0. So how do you compute this? I'm just mentioning this quickly because it took me a few days to figure out that it was actually a very simple calculation. You describe this stretched horizon by just giving a parameterized curve. The coordinates are rho and tau. You just give rho and tau as functions of sigma, some parameter. Given that, it's easy to find the unit tangent vector and the unit normal to this curve. And then the mean curvature, the trace of the extrinsic curvature, is just a tangential projection of the covariant derivative of the normal. In higher dimensions, it's a slightly more general expression because there's more than one tangential direction, but it's still essentially the same. So you just write this out and do the calculation, and it's easy enough, and it gives you some arbitrary looking combination of derivatives of the coordinates of the curve. You stick this into the Gibbons-Hawking boundary action, and you get, again, something that just looks like some complicated integral. Now, let me say a couple of things about this integral before I go on. Suppose that you take this curve to be a circle. So rho equals constant, but rho equals some small constant, epsilon. The second term here is then a total derivative. And if phi is constant, the second term just goes away. The first term looks like a total derivative if phi is constant, but tau is a periodic function, and so you get it integrates to 2 pi. And that gives you, in the limit that your circle shrinks to 0, a boundary term of phi over 4g. Phi is the transverse area. So that's the standard Bekenstein-Hawking entropy. It's area over 4g. And that's how Gibbons and Hawking, well, Gibbons and Hawking actually looked at a boundary at infinity, but you can just as well look at a boundary at the horizon. to get that standard answer. But now let's let this curve be arbitrary. Then this is too complicated. But if we let it be arbitrary with the restriction that the derivative of rho, the radial direction, is small, that is, that it's a wiggly boundary, but that it doesn't actually come all the way into the horizon, then you can approximate this and you get an integral that, again, it just looks like something. The first term here is the standard Gibbons-Hawking area term again. The second term almost looks like a Schwarzian, but it's not quite. And so it looks as if we're not getting a Schwarzian action here. But there's also an ambiguity because the two terms have very different sizes. As long as the stretched horizon is very small, the first term is much larger than the second. And so you can wonder, well, can you shuffle a little bit of the second term into the first and get a Schwarzian derivative? Well, you can, but it seems kind of arbitrary. There is something you can do, though. You can go back and look at the boundary conditions. If you look at the variation of this dilaton action, again, with an arbitrary potential that turns out to be irrelevant for this consideration, you find that there are two conjugate pairs of boundary variables. The dilaton, I'm sorry, I shouldn't say that. There are two conjugate pairs of variables. The dilaton is basically conjugate to the extrinsic curvature, and the metric, H here is the induced metric at the boundary, is conjugate to the normal derivative of the dilaton. If you want to specify boundary conditions, what you have to do, well, the simplest thing to do is to pick one of each of these pairs and fix that at the boundary. You can also choose linear combinations, but let's stick to the simple choices. The Gibbons-Hawking boundary term corresponds to fixing the metric and the dilaton at the stretched horizon. The dilaton is basically the leftover transverse metric. And so that's equivalent to the usual picture of just fixing the higher dimensional metric at the horizon, which is certainly a sensible thing to do. But you could instead fix the dilaton and its normal derivative at the horizon. This at first seems unintuitive because you think of a field and its normal derivative as being conjugate pairs, but it turns out that that's not what happens in this theory. Now, what does this mean? It means, first of all, that the metric and the extrinsic curvature are allowed to vary freely. That is, that we have a free boundary. The other choice is restricting the boundary. It means that what we are restricting is the transverse geometry, if for Schwarzschild or Kerr metric, if you like, the geometry in the theta phi direction, which seems to be a perfectly natural thing to do. In the nearly anti-de Sitter case, it can be shown that fixing the dilaton and its normal derivative corresponds to a microcanonical ensemble. That is, that it's equivalent to fixing the ADM energy of the solution. For the non-extremal case, this is less clear because we're only working in a small neighborhood of the horizon and the ADM energy is defined at infinity. And depends in a complicated way on the details of that dilaton potential. But this is still perhaps something like a microcanonical ensemble. Now, if you change the boundary conditions, you change the boundary terms as well. And it's straightforward to check that in order for the action with these new boundary conditions to have an extremum, you need to add a second boundary term. So now it's just a matter of doing the calculation. We know what the extrinsic curvature is. We know what the normal vector is. We know what the metric is at the horizon. We just do the integrals. When you do that, you get a boundary term that has two pieces. The first is, again, just the standard A over 4G. Only the difference now is that this is the actual area at the horizon, not the stretched horizon. So that's the kind of correct zeroth order term in the action. The second term now is just a Schwarzian action. It's a Schwarzian action in which the variable is tau, which is this angular coordinate or this imaginary time. It depends on the parameter sigma that is the proper length along the horizon. And it's a Schwarzian. Well, it's not quite a Schwarzian. And this is something that I still don't entirely understand. First of all, this part I do understand, that the coefficient is no longer the dilaton, it's the normal derivative of the dilaton, but that's now fixed, so that's not a big surprise. There is also the extra 1 over tau prime squared in the action, which is not there for the nearly anti-de Sitter case. This has something to do with the fact that the Schwarzian derivative is actually a quadratic differential. In the nearly anti-de Sitter case, there is an explicit breaking of reparameterization invariance that's made during the calculation that gets you to the Schwarzian. Otherwise, this derivative, this action wouldn't really make sense because you're integrating d tau, a scalar times a rank 2 tensor, and that's not invariant. But there's a normalization of the scalar that actually breaks reparameterization invariance in a way that makes that all work. No such thing happens in the non-extremal case. And as a result, to get the right transformation properties, you have this extra 1 over tau prime squared. I don't know what that means for quantization of this action. There may be some clever change of variables that makes it go back to a standard Schwarzian. I just don't know. There are also a couple of obvious follow-up questions to this. This is supposed to be a description for a generic non-extremal black hole, but you should be able to take the extremal limit, and that ought to recover the Schwarzian action of Naldacena and his collaborators. I haven't done that yet. I don't know if or how that works, but it ought to be possible. I was asked earlier about the Lorentzian version. This should be possible to do, but it's tricky. for a stretched horizon in the Euclidean case, you want the stretched horizon to remain a small proper distance away from the genuine horizon. In the Lorentzian case, that turns out to be very hard to do because the horizon is a null surface. And if you try to draw a second null surface that's near the first one, it diverges rapidly. So you have to take a space-like surface that in which the proper distance along some natural cuts actually becomes small as you go to infinity because the null surface is spread out. Years ago, I worked out how to do this. It's a mess. So it's certainly worth looking at, but it's probably painful. There's more to understand about these new boundary conditions, the fixing the dilaton in its normal derivative. In particular, there may still be some way of relating this to the ADM mass and making this into a genuine microcanonical ensemble, but this is also something that I've just started to look at. From these canonical pairs, there are 4 possible natural boundary conditions that you can choose. And I've looked at 2 of them. It would be interesting to see what happens with the other 2. There is one recent paper that deals with this question for the nearly anti-de Sitter case, where there's some very interesting results. Some choices of boundary conditions don't actually give you a configuration that definitely has a horizon, for instance. But again, this is not something that I've yet looked at. Okay, so I assumed that I had 50 minutes for this talk, and it looks like I'm just about there, which is pretty good. So let me stop there and ask for questions.
Thank you very much for the very clear talk. Please ask for questions.
Question. Let me consider about symmetry. So in SYK, we know that the saddle point solution. So if I consider some fluctuations around the saddle point solution, we know that the coset manifold of the Goldstone boson is given by diffeomorphism quotient SL2R. So SL2R is residual remaining some symmetry here. So in this kind of derivation, can I see the symmetry of this action? So how can I see the quotient SL2R for, is it invariant under SL2R for this action, or if I consider extreme limit, I don't know, yeah.
Yeah, that's a very good question. I don't know the answer, but I don't think that you have the SL2R invariance. The SL2R invariance from this point of view comes from the fact that the metric for the nearly ADS case is hyperbolic. Here the metric is flat, and it has, so its isometries are the translations and rotations rather than SL2R. Now, I guess you can think of those as they're probably a reduction of SL2R. I'm not sure. So there's certainly the SO2 subgroup of SL2R. And then semi-direct product with the translations, which doesn't give you SL2R. but gives you ISO 2, I guess, which, so I'm not sure. That's a really good question.
So this Schwarzian form probably invariant under the SL2R transformation, as we know, the Schwarzian derivative. But this the term that you mentioned, the what is it? 1 over tau prime square not be invariant. So that may be problematic in the end.
Yeah, that's certainly at least part of what's going on, but I don't know the answer yet. Maybe somebody there can figure this out.
Then
let me
what
know.
does it? Yeah. Then what does it mean if I consider some extreme limit of RNA-DS, for example, RNA-DS black hole, and we know that near extreme limit, we know that the geometry is given by ADS2. Then the effective action, if I follow your Kaluza line reduction, is not identical to the Schwarzian, then had some different type. That's your conclusion with this some new boundary condition.
Well, what goes on there is that this description of the near horizon metric as a flat metric breaks down. That's because for the extremal black hole, the lapse function doesn't go as the square root of r minus r plus, it goes as r minus r plus. And if you stick that in,
I see.
the equivalent here is hyperbolic space rather than flat space. But it's a limit. And so there must be some way of taking that limit as you letting some variables all vary in this at the same time in a way to get that limit. This is a brand new result. Result is only a month or so old, and I haven't figured out how to do that.
I see.
Again, I don't have any claim over this. I welcome anybody else who wants to figure out something like that.
And I have one more question. So usually in the like a 3D or 2D, people talk about the asymptotic ADS condition at the infinity. And there are many studies of that. And here you also study the near horizon geometry. There's some sort of some asymptotic symmetry near the horizon.
I've spent years working on trying to understand the symmetries near the horizon. There is a lot of symmetry. There's a lot of symmetry, but it depends. The symmetries depend on exactly how you define the near horizon limit. The latest thing that I've looked at suggests that there is essentially a BMS symmetry near the horizon in this reduction to two-dimensional dilettante gravity. There's certainly a diff S1 symmetry just from diff S1 or diff R symmetry. So a Virasoro symmetry from just translations along the horizon. There is also an approximate symmetry coming from the fact that the expansion at the horizon is 0, which means that if you move slightly off the horizon to lowest order, a lot of things don't change. And these two combine to give a BMS symmetry, I think. I mean, I have a couple of papers on this, and the referees didn't find anything wrong with it, but I don't think that's quite the whole answer yet.
And is there a relation to the asymptotic symmetry with the Schwarzian, or the nothing to do?
I don't know. I don't know. I think there ought to be, but I haven't had a chance to look at that yet.
Oh, can I ask one question?
Yeah.
Yeah, in the last page of your slide, it's about question about the extremal limit. I mean, let me understand this question. Do you mean that is it about how to go to the ordinary Schwarzian action starting from this stretched horizon chart?
Yes.
Then yeah, I thought that this Schwarzian action was already some beyond the extremal black hole. It's some by wiggling this boundary, and then I thought it's
Yeah.
already away from the extremal limit.
Well, it's the near extremal limit. The nearly ADS structure that analysis starts with, or the reduction, the fact that that you reduce to Jakob-Teitelbaum gravity rather than a more generic dilettante gravity, that comes from the fact that you've already taken the near extremal limit and are looking at this small region near the horizon.
Then
So
I see. Then from the ordinary Schwarzian action to go to the exactly extremal limit, is it well defined process?
from near extremal to extremal. I think it is. I think that this goes back to papers by Strominger, Way, and Hartman about the extremal and near extremal Kerr black hole and the near horizon description of that. And they actually started with extremal and then perturbed that to get near extremal. I think that the only place that directly comes in, I'm not positive of this, but I think that the only place that comes in is that in the extremal limit, you genuinely have an ADS throat. And for the near extremal, you have something that's ADS plus small perturbations.
So I have also another question about here. You talk about the metric-like formulation, but for 3D you have also Chern-Simon gravity. In that case, do you have like a get the same answer, or is there be something might be different?
So in 3 dimensions, there are at least 2, probably more than 2 ways of getting the effective theory. One starting from the Chern-Simons formulation, and one very much like what I've described here, starting from the ordinary metric formulation, but putting a boundary, a wiggly boundary, and looking at the induced action. In both of those cases, what you get is a Liouville action as your effective description. There is a relationship between Liouville theory and the Schwarzian action, but it's one that I only know that it exists. I don't know. It's not something that I've looked at enough to tell you whether it gives the correct relationship.
Is there further questions? If not, let's thank the speaker again.